Welcome back, Nature in Code. We're in chapter 3, and we just started implementing population bottlenecks in our drift simulation. So we just finished implementing this method here, which calculates the effective population size of a set of n's. In our case, this array of n's is just going to be all population sizes over all generations over all simulations. And then this is going to be plotted here or shown here in the legend. What we don't have at the moment is we don't actually have bottlenecks, because if you look at our function next generation that we call in each generation, it still happily uses this value of the population size n here, which is constant. So we don't want that. We want this function to be more flexible. It shouldn't work with this global variable here. It should work with just whatever population size we hand it. And so let's change that. Let's actually have a second argument here that allows us to hand the population size over to this function, and I'm going to call this current n, and then I want the function to work with this current n rather than with this fixed n over here, this global n. So that's all that's changing here in this function. I'm just making it a little bit more flexible by not relying on a global n, a global variable of n, but by having the second argument so that we can pass a value for n, and then it works with that value. And now, so where are we actually calling this function? Well, we're calling this function down here, right, in this loop here in the simulation function. So what we need is we need to pass this the second value here. But before I do that, I now want to implement some code to make this flexible. So what I'm going to do is I'm going to set up another variable here that I'm going to call population size. And I'm not going to initialize it to a certain value. I'm just going to set it up here so that it's defined. Now, down here in this loop, I would like to say something of the following sense. Set population size to n, except every 10th generation, then set it to 10. Set the population size to n, except at every 10th generation, set it to 10. So how do we do this? Well, here's how we do this. We say if I percent 10 equals 9, then, and I'll talk about this in a second, set this population size variable to 10. This is our bottleneck. Else, set it to population size, well, whatever we have defined as this, default population size, if you will, n. And again, I'll talk about this in a second. But in any case, population size is now set correctly, and so I actually want to push population size here to my population sizes array. And importantly, I want to now pass this population size as a parameter to the next generation function. So now, the next generation function will work with whatever I pass it here, and this value is going to be n most of the time, except every 10th generation, it's going to be exactly 10. And once again, I will be talking about this in a second, but just accept now for a fact that this will happen every 10th generation. This condition will be true every 10th generation. So let's save this, okay, and let's go back to our browser here, and let's reload it, and here it is. Voila. This is now a population that undergoes sporadic bottlenecks of size n10. And you can see this quite clearly here. So you can see here's a bottleneck, and then here's a bottleneck, and of course this is true, it's every 10th generation. Here's a bottleneck, and you can also see that these bottlenecks are completely determining or driving, I should rather say, because it's still stochastic, but these bottlenecks are totally driving the dynamics here of the simulation. And indeed, look at this, our function here works. The effective population size is correctly being calculated at 92, even though, right, let's go back to the code, our n here is 1000. However, because of these occasional bottlenecks here to size 10, the harmonic mean will be correctly calculated as 92. And indeed, right, this looks much more like the simulations we had before with a constant population size of 92. So it's important to reflect what this means, and if you understand this, you really understand effective population size, right? We have a population here that has size 1000, but every 10th generation it only has size 10. So you could be forgiven to think that, well, the average population size is 901, and so you would expect this population to behave like a population of a constant 901 size. But that's not what's happening. This population behaves like a population that would have a constant size of 92. And so this is what this effective population size captures. The effective population size here is 92, which is the harmonic mean. And you can see that this population indeed behaves like a population of 92, a constant population size of 92. Now, let's go back to our code and try to understand what this means here. So recall I here is simply the counter that we set up here for this loop. So it's 0 at the beginning, and then it will be incremented by 1. This operator here is the modulo operator. And it's actually quite easy to understand what it does. The modulo operator simply gives you the remainder of the integer division, the integer remainder. Okay, let's go back to the browser, open the JavaScript console here, and see what this is. Okay, so let's start with 0% 10. Now so the way to think about this is simply, okay, what is 0 divided by 10? Well, it's 0. And what's the remainder? Well, it's still 0. So this should be 0, and that's correct. Okay, let's go to the next example. 1% 10. So what is 1 divided by 10? Well, it's 0, but now it has a remainder of 1. And correspondingly, this will be 1. And so on, right? 2% 10. Oops, sorry, 2% 10. What is 2 divided by 10? Well, it's still 0, but now it has a remainder of 2. And so on, 3% 10 is 3, 4% 10 is 4, and so on. So interestingly, now let's go to 9% 10. 9 divided by 10 is still 0, but the remainder now is 9. 10% 10. Okay, 10 divided by 10, that's now 1. And it has 0 remainder, right? And indeed, this is now 0. And so 11, same thing, right? 11 divided by 10 is 1, remainder 1. So this gives you the remainder. And as you can observe, if you would continue to do this, this would always be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then again, it would be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on. And so basically what this here means that whenever this remainder is 9, then do something. In our case here, implement this bottleneck. And this will be 9 exactly every 10th generation. So at the beginning, 0, when I is 0, the remainder will be 0. And then in the second step, when I will be 1, the remainder will be 1, and so on. And at the 10th step, when I will be 9, the remainder will be 9. And that's when we have to implement the bottleneck. And then again, the next time this is going to happen is when I is 19. Okay, 19 remainder 10 is again 9, and so on. 29 remainder modulo 10, also remainder 9. So that's how this modulo operator works. And by the way, you could really put any number here, right? You could put 5 here. In this case, when I is 5, or when I is 15, right? 15 modulo 10, yeah, is 5. When I is 25, 35, and so on, this would also work. It would also be every 10th generation. It's just that the initial 10th generation would be at, you know, the slightly wrong position. And so I'm putting 9 here so that it is actually perfectly at the 10th position, so that first you have 9 generations of no bottleneck, and then you have 1 generation with a bottleneck. But this could be any value. I'm just putting 9 here so that it does it correctly right from the get-go. All right, so this concludes this video. So we've implemented here a bottleneck version of our stochastic drift simulation. Maybe before we close, I want to do one more thing. I actually want to take a look at what the situation would look like if our default n would be much larger. So I'm going to increase that by a factor 100 to 100,000. So what does this mean? Well, it means that our population will have the size of 100,000, which is quite large, but then every 10th generation it will collapse down to 10. What does this look like? Well, let's do this. Let's just reload it. Takes a little longer here. This is what it looks like. This looks really neat, doesn't it? You can see that the effective population size now is exactly 100. And so this population does not at all behave like a population of an average close to 100,000, right? Because then, you know, you would have practically no drift. You would barely see anything over 100 generations. Indeed, you see quite a bit of genetic drift, and you already have 2 cases where the allele has gone to fixation. Here the A1 has gone to fixation, here the A2 has gone to fixation. And you can, I think this particular simulation, or these 10 simulations, really bring home the point quite nicely that in this case, the dynamic is completely, the genetic dynamic is completely driven by these bottlenecks. And so I hope this explains why these bottlenecks have such a huge impact and why the effective population size is going to be so substantially reduced. All right. Well, that concludes this bottleneck implementation, and I'll see you in the next video.